Our next topic area is going to be Schmitt trigger circuits. And so what we're going to see is our Schmitt trigger is actually a type of waveform generator. And this waveform generator is actually using positive feedback, unlike most circuits that we'll talk about which use negative feedback. And so if we want to get more specific about what type of waveform generator it is, we can actually classify our Schmitt trigger circuit as something called a bistable multivibrator. And so what that means is it's going to have two stable output states. And so both of these are ideas that we're going to come back to a lot in later topics. So we're going to come back and we're going to talk about this idea of positive feedback in our feedback and stability section. And we're going to come talk about other types of waveform generators called oscillators. And so we're going to talk about astable and monostable as well. But for now, just to kind of tie that into where we're going. So before we actually look at what a Schmitt trigger circuit is or what it does, let's first talk about some of the basic components as well as sort of the need for a Schmitt trigger circuit. So we're going to start by looking at a comparator. So we're going to consider a comparator. And so our comparator is essentially just a op-amp that's operated in an open loop configuration. So if we have our op-amp in an open loop configuration, we don't have any feedback coming between our output and our inputs. So recall, for our op-amps, we have an inverting terminal, a non-inverting terminal, both of which are inputs, and then we have an output terminal. So what we're not showing here is, of course, we also have our bias terminals, which are giving power to our op-amp. So let's label the inputs VI and VREF for reference voltage. And so we can think about this reference voltage being a fixed value, and VI, our input, is changing. And so if we want to do that, then we could plot what our output voltage Vout looks like as a function of our input voltage VI. So let's say in this case we happen to have a positive VREF. So I'm going to put my reference voltage right here. So that's our VREF. And so let me just, for abundance of clarity, let's just come down here and say that VREF is greater than 0 in this case. So what's going to happen is, if we remember our ideal op-amp model from previous classes, we're essentially taking the difference of our two inputs and we're amplifying that by some really large gain in our op-amp. And we said that, of course, if we have these large gains and they're multiplied by something, we're not always going to realize that. For instance, if we have a differential input voltage of 0.1 volt, but our gain for our op-amp is on the order of 10,000, well, of course, we're not going to see that on our output because we're limited by the rails or the power supplies of our op-amp. So instead, what we're going to do is we're going to have the op-amp going into saturation. And so we're going to call those levels, for instance, up here for our high level, we can call that VH. So this level here, let me switch back to black and we'll label this, we can call VH for V high. Similarly, we're going to have a level down here, VL. And so the operation of this comparator is, so long as our input is less than the VREF, we're going to have a positive output. We're going to be saturated at V high. Now, once we cross over VREF, what's going to happen is, and so that should be going through our VREF, we're going to come down here to our V low value. And we're going to stay there at V low so long as our V input is above VREF. And so, of course, these are going on towards negative infinity and positive infinity for our input values of VI. So again, the VH and VL are our saturated outputs. Switch back to black here. So VH and VL are our saturated output voltages. And so again, like we've talked about in previous classes, typically these will be somewhere near our supply voltages, which I've not drawn explicitly, but we could draw V plus and V minus. So they're not going to be exactly these values, but they'll be close. So for instance, maybe if this is 5 volts, we might see that our V high is 4.8 volts. So something along those lines. Okay, so now we want to look at the sort of problem that our Schmitt trigger is going to be addressing. So let's say we take this comparator circuit and we're going to use it to control a street light. So let's consider comparator to control street light. And so what we're going to do is we're going to add some other components in here as well. So let's copy this circuit that I've got ready ahead of time, and we'll put it right about here. Okay, so notice what we have. We have our comparator sort of in the middle. It's the op amp, and we know it's a comparator because we don't have any feedback. It's operating open loop configuration. So we have a photo detector circuit over here on the left, and so what's going to happen is, of course, we're going to have some light coming in. So we have some photons. So this is our light. And by whatever means, we're saying that this photo detector circuit is going to convert that light into a voltage, VI, which becomes our input. So now see, this part here looks very similar to what we just looked at. We have our VI, our VREF, and our Vout. We've just given a physical definition to our VI. So now we notice the output is connected to the base of a BJT transistor. And so on our transistor, off the emitter, down here in the bottom, we have a resistor, a diode, and a relay switch, which is going to our light control. And so basically how this is going to operate is that if we have current through this relay switch, we're saying we're going to turn the lights on. If we don't have current, we're going to turn the lights off, or we're not going to turn them on. So of course our resistor is going to be helping us bias that transistor and to help us limit current. And then our diode is included here to prevent reverse breakdown of our BE junction. So prevent breakdown of our BE junction in the transistor. So for whatever reason, say our transistor is turned off and maybe this relay switch is trying to kick some current back up into the transistor, well, that diode's not going to allow it, because remember, the diode is only going to allow current to flow in one direction, and it's in the direction that that triangle is pointing. Okay, so considering the circuit, let's consider our two sort of extreme cases. Let's say we have a really sunny time during the day. So sunny daytime. So what that's going to mean is that our photodetector current is going to produce a really large input voltage. So we're going to have VI greater than VREF. And so based on what we saw with our simple comparator circuit up here, we know if VI is greater than VREF, we're going to have a low output. So we can come down here and we can say this means we have output is V low. And so what that means is if our output is low, we're not going to have a large enough base emitter voltage. So remember, we could label this as our base emitter voltage. So if our base voltage is too low, we don't have enough voltage to turn on the transistor. So when we have Vout is VL, we have that our transistor is off. And so we can think back to the physics of our transistor, or you can just kind of think of a transistor as being a simple switch. And so when the transistor is off, it's not going to allow any current to flow through in this direction. So no current flowing through our transistor, no current coming out the emitter, means we have no current in our relay switch, which means our lights are going to be off, as we would expect. So no current in relay switch, which means our lights are off. Okay, so our other extreme, of course, would be if we are in the middle of the night and maybe there's no moon, maybe there's a lot of cloud coverage, so it's very dark. So in this case, we don't have any photons, or not nearly enough photons coming in to create a large VI. So we have our VI is less than VREF. And so we could think about our simple comparator circuit, and in this case, that means our Vout is going to be V high. So now that we have a high input voltage to the base of our transistor, we're going to have sufficient value to bias our VBE in the forward bias mode, so we turn the transistor on. So now our transistor is on. And so what that means is we're allowing current to flow out of the emitter. We're going to have current in our relay switch, and our lights are going to be on. Okay. So you might be saying to yourself, well, isn't that exactly what it should be doing? It seems like, everything is working perfectly fine here. What's the issue? So let's make one small change. So let's add some noise to the system. And so this noise could represent a couple things. It could represent maybe there's some slight cloud coverage. Maybe it's covering the photosensor at a certain time. Maybe there's a tree that's moving in and out. Maybe a bird has built its nest on top. So various things that could be happening. And these things are going to be particularly troublesome, we'll see, around sort of our transition points, which if we're talking about day and night, would of course be dusk and dawn. Okay, so where are we going to add this noise? Well, let's come up here and add it between our photo detector circuits. So say we produce some photo signal, let me make this a little larger. We produce some signal VI corresponding to our light, but now we want to have this signal, which maybe is noise produced in our cable. And so we'll talk a little bit about noise in cables at a later point as well. But we have this noise signal here, V sub m. So how is that going to change things? Well, let's take a look. So the easiest way to see this is graphically. So let's say we have over time. Here is our reference value. So this point right here is our Vref. And the reason I'm sort of highlighting this Vref on our voltage scale is because, of course, that's sort of our transition point. We said if we're above Vref, our lights are off, and if we're below Vref, our lights are on. And so here we're plotting over time. So let's say our input voltage, which is corresponding to our light, looks something like this. So maybe we have, and let me actually do this a little bit steeper, so this next part is going to be easier to draw. Okay, so let's say our input voltage corresponds to this. So this is our VI. So sort of down there at the start of time, we have a low input voltage, so that would correspond to it being dark. And then over here on the right, our light is getting brighter. So this would be like day and night. Okay, so now if we add this noise signal though, of course our noise is going to be random, so we're going to sort of be going up and down off of this signal. So maybe we have something like this, and it's just sort of randomly going up and down. Maybe we have something like that. So it looks something like that. And we can call this our VI primed, our new input, which is composed of our input and our noise. Okay, well, let's look at what our output looks like in that case. So let's put another graph sort of right below this, and we're going to line up our time axes. So here we have our output voltage, and here we have our time as well. And so again, I'm going to draw some lines down to indicate our time. And we know our output voltage of that comparator is going to take on one of two values, either our high saturated voltage VH or our low saturated voltage VL. So we had said previously, if our VI is less than Vref, then our Vout is high and our lights are on. So let's take a look at what that would be. So we could actually, let's draw down to here. So we see that our Vref, we're not exceeding that Vref until this point right here. So we can say, all right, at this time, that time is where we are above Vref. So when we transition above Vref, we are going from high to low with our output voltage. So up until this point, we were V high because our input was less than Vref up here. But once our V input, which really we're talking about our V input primed, goes above our ref, now we go to V low. So we're going to transition to V low. So now we're down here. Okay. So now we keep on moving along this curve, and we see that, oh, well, actually, we're moving along this blue curve here, and we see that actually after a little bit of time we're going back below Vref. So let's come down here, and so what that means is going to happen there is we're going to come back up to V high. So now we have been at V low for just a little while, but now we come back up to V high. And so you can see we're going to have this similar issue where, again, we're going to cross here. So we're going to transition again there to V low. And then we have a couple more crossings here as well, which are going to be transition points. Okay, so let's just fill this in and then we'll talk about what this actually looks like in terms of our output. So here we would transition to low, and then at this point we would transition to high, and then at this point we would transition to low, and beyond that point we're always above Vref, at least for what we've shown, so our output stays low. Okay, so remember when our output was high, that corresponded to the lights being on. So up here, we're saying our lights are on. And for V low, we're saying our lights are off. So what this means physically, if we constructed this system, is that our lights would be flickering on and off in this area right here. And so obviously that's not ideal for a few reasons. Of course, you just don't want to have flickering lights. Maybe it's by a street, that could be distracting to drivers. Number of reasons, power considerations and such as well. So the way we're going to fix this problem is with our Schmitt trigger circuits, and so we'll see how to do that in our later videos.